Welcome back. That's our video lecture number 3 of week 11 of Graduate Statistics, University of Cincinnati. So we're working on a challenge based on data reports on police shootings in 2015. The data shows that more white individuals are killed by policemen than black individuals. And the hypothesis that somebody may raise based on this data is that racial bias in police shootings, the hypothesis of racial bias in police shootings is just false. And our challenge is to show that this is a simplistic conclusion based on data. And we'll use then the chi-square test to demonstrate why this conclusion is really a serious misconstruction of the data or a naive interpretation. So for us to do this, we will need to get census information about race distributions in the US to put the data into context. Raw counts will not help, just like they didn't help in the previous example. And then we'll compute the number of shootings by race that would be expected if shootings were unrelated to race to create a descriptive table. Then we'll use the chi-square test for goodness of fit to determine whether race is a significant factor in determining police shootings. So let's check that distribution. So I went to the census data of 2016, more or less at the same time of the reports on the police shootings. I got the closest I could. And we see that Black or African Americans alone represent 13.3% of the population. Hispanic or Latino, 17.8%, and white alone, white people that are not Hispanic or not Latino, 61.3%. Okay, if we sum all of these, then we'll leave 8% for other. Okay, and we leave 8% for other, again, because as we sum all of these things, it turns out to be 92%, and we need 100%, so we add 8% for other race or ethnicities. All right, so here are our hypotheses. No hypothesis, nothing is going on. The observed counts of police shootings per race ethnicity follow the same distribution of the population. And the alternative hypothesis is that there is bias, and the observed counts of police shooting per race ethnicity does not follow the same distribution in the population. So here's our table. This time we have 4 different categories: white, black, Hispanic / Latinos, and other or unknown. So the sum, the total number of shootings was 995. What would be the expected? Well, we use the percentage of the different races and ethnicities in the population to compute that. So if the sum is 1995 and there is a proportion of 61% in the population that are white, and if the number of shootings were completely randomly distributed across the different races, then we would expect 606.9, let's say 607 individuals, white individuals being shot. We would expect, based on random processes alone, that 132 black individuals would be shot, 179 individuals would be shot, and 80 individuals of other or unknown races would have been shot, right? So we're using the 61%, 13%, 18%, and 8% that we got in the census data, okay, to compute these things. So we have the total number of shootings, and we multiply that by the proportions of white, black, Hispanic / Latinos, and other / unknowns. All right, then we compute the deviation of observed from expected for all of them. Then we compute the squares of these deviations to make everything positive. And finally, we take every one of these square deviations and we divide by the expected to get those values. Then we sum all of those square deviations divided by the expected count, and we get the chi-square statistic, which is kind of the overall squared deviations in proportion to the expected. And we need then the degrees of freedom of the chi-square distribution that we need to select, and that's 4, because we have 4 categories this time, minus 1, which is equals to 3. And then we need to get the probability of getting a chi-square statistic of 143 with 3 degrees of freedom of the distribution. And again, we set lower tail to false because we want the upper tail, and that is a very tiny number. You'll see in the lab, definitely less than 0.05. I think the cutoff for 3 degrees of freedom is between 7 and 8. So way above the 0.0, way less than 0.05, the probability of observing this deviation if there was no bias in police shooting. So this allows us to come in and say, I'm going to reject the null hypothesis that nothing is going on. And I am going to assume that there is bias, because the observed counts of police shootings per race and ethnicity does not follow the same distribution in the population. And I can say that the bias is primarily against Black individuals, because if you look here, the expected number, if shootings were not affected or not influenced by race, would be 132, and you have almost twice as many Black individuals being shot than would be expected by chance alone, right? And the opposite happens for whites. Take a look at this. The expected number of white individuals being shot by police, if these shootings were not related to race at all, would be 606 or 607. Way less white individuals are shot than would be expected just by chance, right? So really, policemen seem to be less likely to shoot white individuals than Black individuals, and this data provides very strong support to this assertion. Now let's move on to a slightly different kind of problem that chi-square can help us with. Finding relationships between categorical variables. So let's see another problem. Racial bias and the death penalty. We could have 2 hypotheses here. You know, there's nothing going on. Race and your chance to get a death sentence are completely independent. The rate of death sentence does not vary by race. And the alternative hypothesis here would be that race and death sentence are dependent. The rate of death sentence varies by race. How would we evaluate this hypothesis? We estimate how different the observed counts are from the expected counts, considering chance alone, and determine the likelihood that one would see the estimated difference between expected and observed counts if only chance was at play. So these 2 steps seem very similar to what we've done before. The difference here is that we'll run what we call a chi-square test for independence, because differently from the first 2 problems, where we had only one variable, which was race, and we counted, first we counted number of juries in each race, and then we counted number of police shootings in each race. Here we have 2 variables. We have the race and we have the death penalty. So you were looking at the likelihood of these 2 things, these 2 separate things, the likelihood of getting the death penalty and how that's modified by race. So we have 2 things going on here at the same time. So what we want to know if these 2 things are independent or if they are dependent. Now, to be able to estimate how what the expected counts are so that you can estimate the difference between observed and expected, we need a little bit of probability theory that I will use to explain to you how we get there. And the law that is of interest here is the probability multiplication law. Now, what this law says is that if A and B are independent events, imagine A is the death penalty sentence and B is race, if your likelihood of being a particular race and your likelihood of getting a death penalty are completely independent events, then the probability of joint occurrence of A and B, the joint occurrence of a particular race and the death sentence, is equal to the product of their individual probabilities. So the probability of A and B happening together, right, if those two things are independent, is equal to the probability of you being a particular race times the probability of you getting the death, of someone getting the death sentence, okay? If two things are independent. Let's see an example. One situation that we know for sure there is independence. Distribution of colors of little candies in M&M bags, okay? We know that, you have 13% of brown, 13% of red, 14% of yellow, 16% of green, 20% of orange, and 24% of blue. So the probability of you getting, if you pick one, the probability of you getting a brown candy is 0.13. The probability of you getting a red candy is 0.13, yellow 0.14, green 0.16, orange, blah, blah. Okay? Now, if you want to know the probability of getting, if you pick two, probability of getting a brown and a red, the joint occurrence of these two, if you pick two, the probability of it being brown and red, because, your probability is one probability is completely independent from the other, we know there is no correlation between them, should be the probability of you getting a brown times the probability of you getting a red. So here is this. Because the probability of you going into the bag and getting a brown M&M and getting a red M&M, we know that those events are independent, because once you get the brown, there is no more extra chance of getting red, right? Because this is truly random. Would be equal to the probability of you getting white and you getting the brown and you getting the red, which is 0.13 times 0.13, then you can compute the joint probability, okay? Same thing, what's the probability of getting the green and the blue? Because those two are independent, you can compute that probability by multiplying 0.16 by 0.24 and getting and knowing that the probability of getting these two things together, the joint probability, is 0.04 approximately. Now, how do we apply that to our situation? Here's how. We calculate the expected counts under the assumption of independence, under the assumption that the null hypothesis is true, right? That's what we want. If we assume things are random, here we have our contingency table. We have race here and we have the death sentence here. So here are the number of people in a period of time that got the death sentence, and that's 66, and the number of people that did not get the death sentence. So once you committed a crime, so here's the problem. You committed a crime and you go to court, okay? We had 825 of those cases represented in this table. 66 of those cases got the death penalty. 759 of those cases did not get the death sentence. Of those individuals, 825, 284 were non-white, and 541 were white. Okay, so given that there is this, given this data, can I compute what is the probability under the assumption of independence of being non-white and getting the death sentence? What's the probability under the assumption of independence of being white and not getting the death sentence? We can use that product, because when things are independent, that's how you compute the probability. So you can get the counts using the probability law of multiplication, okay? So here in the table in black, we have the observed numbers. And we're gonna write in blue in this table the expected numbers that we're gonna calculate together through the application of the multiplication law. So we're going to get the expected counts under the assumption of the null hypothesis, okay? Because then the deviations can tell us if there is bias or not. So let's do this cell here first. The probability of getting the death sentence times the probability of being non-white, because that would be the probability of getting these two things together, non-white race and death sentence, under the assumption that race has nothing to do with death sentence. So that would be the probability of getting the death sentence is 66 divided by the total number of cases being judged. And the probability of being non-white is the total number of non-whites, and 825, which is the total of people being judged, okay? If I multiply these two things, I get about 2.7% of cases should be in this particular cell, right? So I can compute the expected number of non-whites that would get the death sentence if only chance was at play, if race and death sentence had nothing to do with each other and were independent, okay? That would be the total number times that expected probability. So that would be 22, rounding, okay? Now let's do the other cell. Cell 1.2, first line, second column. That's the probability of not getting the death sentence once you are being judged, and the probability of you being non-white if you are in court, okay? So the probability of not getting the death sentence is the total number here, 759, divided by the total number of people being judged. And the probability of being non-white is, again, the total number of non-white individuals divided by the total number of individuals being judged. And that is about 32%, 0.317. So we can compute the expected number in this cell in case of independence, because this multiplication here just works in the case of independence, right? So we can compute here by multiplying that percentage by the total number of people being judged. And we do it there. We will continue to do that for the other cells as well. Let's do this one here, the second row of the first column. We have here the probability of getting the death sentence and the probability of being white. So the probability of getting the death sentence is 66 divided by the total. And the probability of being white is 541 divided by 825. And that will be 5.2%. So we can get, what's the expected count here by multiplying the proportion by the total number. So that would be 43. And then finally, for the last cell, we can get the probability of a person not getting the death sentence, which is this cell here, the probability of not getting the death sentence and being white, the joint probability. We can compute through this multiplication under the assumption of independence, right? So if things were independent, the probability of being white, of not getting the death sentence, would be 759 divided by 825 times the probability of being white, which is 541 divided by 825. And that's 60.3%. So we can compute the expected here again, once more with filling, by multiplying the proportion by the total number. So now we're ready to compute the deviations of observed from expected under the assumption of independence, right? So remember, even if things were independent, you would not expect these numbers to be exactly the same, right? Even if it's true that death sentence and race have nothing to do with each other, are unrelated, right? That your chance of getting a death sentence when you go to jury and your race have nothing to do with each other. Even if we would not expect these two numbers to be identical due to sampling error and other factors that might be interfering with these court decisions. What we need to know is whether these differences here are large enough for us to conclude that they are unlikely under the assumption of independence. If they are unlikely, then we reject the hypothesis of independence and we accept that there is some relationship between these two things, right? And looking at the numbers here, we can clearly see that the expected number of non-whites under the hypothesis of independence is smaller than the number that's actually getting the death sentence. And the expected numbers of whites that would get the death sentence is actually larger than the numbers that are actually getting the death sentence, right? And the opposite's true on this side. Okay? The expected number of non-whites not getting the death sentence is actually larger than the number of non-whites that are actually not getting the death sentence. So if these deviations are large enough to be unlikely under the null hypothesis, we can conclude that there is a relationship between death sentence and race that is biased against individuals that are not white. Okay? We'll come back and compute these deviations and examine the hypothesis we started with. Okay? See you in a bit.